Okay, great. This is the last session of today. Hope you are not boring. Okay, so here's the agenda. I'm going to go through the problem statements, then followed by performance comparisons, and then some details on the techniques. So what's the problem? So as we know, VPP is pretty good, right? Have very high performance, but we think it still have some room can really improve performance. So as we can see that the workload can essentially be categorized into NFV workload and enterprise workload. So we are talking a lot about the NFV workload, VNF or CNF, but we are really talking about an enterprise workload. So the first question will be, can we really improve the NFV workload further? So we will give our experiment data so you can see our answer. And another thing is that as we have so great data path technology to boost performance of NFV workload, can we really apply those techniques to really boost performance of enterprise workloads? So for now, we know the two dominant high performance virtual switching are OVS DPDK and the VPP, but neither of them are really handle enterprise workload great. So from those two questions, we did our experimental to show how we can improve both NFV workload and enterprise workload further. So before we go into the details, let's see some interesting performance data. So this is for NFV workload. This is for VNF, not CNF. So essentially, as a topology, we can see that we're using the T-Rex as a traffic generator, and the VM is running test PMD and with two volatile VNICs. So as we can see, the performance data, VPP is the red one, and VPP C is what we did the enhancement. As we can see, for different size of pack, we have different kind of improvements. Essentially, for the full MTU size workload, we can essentially probably 60% improvements in that regarding. So, but this is just for VPP. It's not for memory if. But for memory if, we believe we can apply the same techniques here. This performance data for VNF. The next one is for enterprise workload. So the first one is the two VMs running on the single host. And we're just using IPerf 3 to test the throughput. As you can see that for VPP, it's kind of 8 gigabits per second. And for VPP-C, it's pretty close to 50 gigabits per second. And for cross-host, for native, the second one is cross-host. We're just using native one, linked by 40 gig links. So as we can see that VPP-C can get more than 30 gigabits per second, much larger than VPP current high. And the second one is VXLAN. The same thing here. So from the experiment data, we can see there definitely have some rooms to improve the performance. So what's the techniques behind the scenes? So I'm going to spend most of the time on this slide. So a little bit history is that for CloudNetEngine, we actually started working on OS DPDK. As we know, OS DPDK probably earlier published than VPP. So there are a number of components from CloudNetEngine switching stack. And the bottom, the light blue one, are some components not really suitable, applicable to VPP. For example, the dynamic scheduler, which means that for a particular receive queue, we can calculate its load, then dynamic scheduling to different worker thread. But VPP has its own scheduling, so it's really hard to apply our mechanism to VPP. And adaptive polling, VPP also have adaptive polling. So the bottom line, we just forget about them, and we just apply the blue one at the upper layer. So you can see the first one will be high performance volatile backend. So right now, as we know that the VPP has a native volatile backend implementation, but there still have some room to improve the performance. The most critical thing on the volatile backend is that there are a lot of cache miss here. So we need to really make that, try to avoid as possible as we can. And another thing is that right now, VPP doesn't really have the offloading. The volatile doesn't have the offloading capabilities. So we need to check some or TSO offloading in volatile backend. The second one is zero copy. The TX zero copy. We know that right now VPP just do a full copy from the volatile front end, and then copy to its own memory, and then send out to the physical wire. So zero copy, the most complex thing about zero copy is essentially right now in VPP or DPDK, there is no comprehensive packet completion mechanism here. So most of the packet just run to completion mode. So especially for volatile backend, when we do full copy, there is no problem since we just release a volatile run descriptor. But if we do zero copy, that means we need to hold on the volatile descriptor as we finish the whole packet logic. So that's going to be much more complex. So that need to have a DPDK to enhance DPDK to really support zero copy. So back to this slide, actually for VNF workload performance improvement, most of the benefit are from the top to one. The high performance volatile backend and the TX zero copy. And for enterprise workload, the techniques are the following ones. For instance, as we can see, we're using a unified architecture to support both NFV workload and enterprise workload. We need to have some sort of unified TX function. So for now, in DPDK, we know that, let's say for NFV workload, it's using a dedicated TX function. For full feature TX function, you're just using a more comprehensive TX function. Those two are totally exclusive. So you cannot use using both of them at the same time. So we need to have some sort of unify. The next thing will be the offloading. As we know, for enterprise workload, TSO and checksum offloading, and also tunnel offloading, we must have this. And also, on the receive side, we need to have some sort of RRO. So the top two are for VNF performance improvement, and the below one actually for enterprise workload. And we implement both of them in the same code base. And we don't need to switch modes, say, hey, this is just for NFV workload, this is for enterprise workload. Just the same exactly the same configuration to support both of the workloads at the same time. Okay, there's some additional thoughts. So VPP, we found that the packet tracing is really great. So let's say in OVS DPDK, if there's some problem, it's really hard to tracing. What's the root cause of the problem? The second one is vector size. As we know that by default, VPP using 256 as a vector size, but it's not really the optimized vector size for real traffic load. So we found that in our setup, most of the cases that 64 vector size is a good one. Let's say for OVS DPDK, essentially just using 32 vector size. One more thing is that about the thread synchronization. So there is a problem when we considering to do adaptive scheduling in VPP. It's a little bit hard than we implement in OVS DPDK, since right now there's no RCU mechanism in VPP, and we have to do a hard synchronization among all of the threads. So that's a problem here. So going forward, and we can apply the techniques we use in the Vertile actually to most of the VPP interface, let's say type v2, memory if, and also possibly apply to host stack, since right now host stack is not really support TSO and RRO. And also using SIST to do performance verification. And soon we will release a beta for VPP, saying based on a stable VPP version. So it's a pretty quick presentation. I will leave some time to take questions. Any questions?
Do you have the intention to upstream some of the optimizations you've made to FIDO VPP?
It depends. So we sure we will seriously consider this approach. No, any more?
Any other questions?
Can you talk a little bit more about thread-heavy synchronization?
Sorry?
You mentioned about thread synchronization being heavy. Can you talk a little bit more about on that? I think if you can go back to your slides. One more. Yes, the thread synchronization is very heavy. I quite didn't understand that.
So right now, let's see, when you do any sort of configuration, all of the work threads have to each other, and they need to have a hard synchronization to apply this configuration change. That means that it's hard. So actually, when we're doing OVS DPDK, we have our own control synchronization. We're using RCU, and then we can only touch the thread which is impacted. So if the threads really not bothering with this particular configuration, it just continue going on. So that's a big difference, right?
Can you not do per thread data structure and therefore avoid barrier sync?
We didn't take a deep look at that approach since in our experimental. We didn't really implement our own scheduling here. So probably, but I think if there is no RCU mechanism, it's going to be hard. But essentially, you have to figure out this particular configuration, which threads are impacted by this particular configuration, right? So, but I don't know if, yeah, so right now, I think all the threads just share the same configuration, right? So you have to decoupling that. So probably okay, but I need to take a close look.
Great. Thank you, Jun.
Okay, thank you.